In the first two mini-lectures for Chapter 11, we'll introduce gases, their properties, and the fundamental laws that describe the relationship between the properties of gases. When first learning about gases, it's common for students to focus on the mathematical relationships between gas pressure, volume, temperature, and the number of moles of a gas. And this chapter will be filled with many simple equations, and sometimes choosing which one is most appropriate for a given situation is more difficult than plugging and chugging given values into the selected equation and completing the algebra needed to solve for the unknown variable. So, it is also crucially important to remember to focus on the concepts that explain why these properties are connected, so that it becomes easier to assess any given situation and make sense of the answer you calculate. We'll start by establishing some of these relationships and talk more about them towards the end of the chapter. So, this begins with taking stock of the unique properties that gases exhibit. Unlike solids and liquids, gases are highly compressible, meaning that external forces can be used to decrease the volume of a fixed amount of gas, thereby increasing its density. Gases are also thermally expandable. When a sample of gas is heated, its volume increases, whereas when it is cooled, its volume decreases. We'll learn about how this is related to the speed of the gas particles towards the end of this chapter. Gases have a much lower viscosity compared to liquids and solids because the distance between molecules is much greater in a gas than in a liquid or a solid. So the molecules rarely interact with each other under most conditions, and therefore they can slip and slide or flow past each other much easier. The greater distances between the molecules also affect the density, with most gases having a much lower density compared to solids and liquids because a small amount of mass can occupy a large volume with a gas. And since the volume of the gas can change through compression or thermal expansion, this also means that the density of a gas varies over a greater range of values than in liquids or solids. Yet another result of the large distances between molecules is that gases are infinitely miscible, which means that any two gases can be mixed together in any proportion, unlike liquids and solids, which are limited by solubility rules and the like dissolves like rule. Since the gas molecules don't get close enough to interact with each other, there aren't any physical forces interfering with or encouraging their ability to mix. So homogeneous mixtures of gases are common and easy to produce. In fact, the air we breathe is a perfect example. Next, what exactly is gas pressure? Well, it helps to think about what's happening on the molecular level. Gas molecules are in constant motion at any temperature above absolute zero, and when the molecules collide with the walls of a container or another object, the force of the collision is what creates pressure. So we can quickly start to see that the pressure of a gas is going to depend on the number of collisions and how much force is involved in those collisions. The physics definition of pressure is the force per unit area. So recognizing that force has units of newtons and area has units of meters squared, we get a unit of newtons per meter squared for pressure, which is also referred to as simply pascals. And pascals is the SI unit for gas pressure. Most of us are familiar with the term barometric pressure from listening to weather forecasters, but you've probably never put much thought into how the pressure of the atmosphere is measured. Consider an open glass tube that is partially submerged in a basin of liquid mercury. The pressure of the atmosphere is felt by this system as gas molecules in the air collide with the surface of the liquid mercury on both the outside of the tube and on the inside of the tube because it's open to the atmosphere. Therefore, nothing really changes with the system as there is equal pressure being applied across the entire surface of the liquid mercury, both on the outside and on the inside of the tube. Now, at sea level on a clear day, the pressure that's exerted by these gas molecules in the air is referred to as 1 atmosphere of pressure, which is equivalent to 101,325 pascals of pressure. Now, if we change this apparatus slightly and instead make the glass tube closed at the top and only open at the bottom where it is submerged in the liquid mercury, and we also make sure that the inside of the tube is completely empty, so no molecules of any type are present, then essentially a vacuum would exist inside the tube. So when the 1 atmosphere of pressure presses down on the outside surface of the liquid mercury, it has enough force to push liquid mercury up into this empty tube, overcoming gravity as it flows upwards. As the height of the column of mercury inside the empty tube gets higher, it exhibits its own force due to gravity. And when that force matches the 1 atmosphere of pressure being exhibited on the surface of the mercury outside the tube, then the mercury stops climbing and the height can be measured. This device described here is referred to as a barometer, and the height of the column of the mercury is what we measure to determine the pressure being exerted by the atmosphere on the surface of the basin of the mercury, so on the outside of the tube. Since the force due to gravity of the column of mercury will always match the pressure being exerted by the atmosphere on the outside of the tube, then the height of the column will change with atmospheric pressure. A device such as this will give a height of 760 millimeters under 1 atmosphere of pressure, and this sets the relationship between the units of atmospheres and the units of millimeters of mercury. The millimeter of mercury unit is also referred to as torr after the inventor of the barometer. So 1 atmosphere is also equivalent to 760 torr, and 1 torr is equivalent to 1 millimeter of mercury. This slide summarizes all the common units of pressure in the different science fields and their relationship to 1 atmosphere. Note that most of these units are used in chemistry, with the most popular unit in chemistry being atmospheres, followed closely by millimeters of mercury or torr. Finally, there is one other device for measuring gas pressure that is similar to a barometer, but more applicable to measuring samples of gas in the lab. This device is called a manometer, and it works by the same principle as a barometer. On the left, a sample of gas at a certain pressure is contained inside a flask and exerts pressure on the surface of the mercury at point B. The force of the pressure from the gas pushes the mercury up the tube on the right until the height of the mercury gives a force due to gravity that matches the pressure of the gas. To measure the pressure of the gas, we simply take the difference in the height of the mercury column with the starting point at point B. This concludes the first mini lecture for material from Chapter 11. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.